Greetings. In the previous video, we made an assumption in the first law that the inlet and exit velocities for a throttling valve are the same, and managed to simplify the first law of thermodynamics to a very simple conclusion that Hi equals He, which means that although the pressure changes at the two sides of the throttling valve, and also the temperature changes, but our assumption was that the velocity remains constant, and therefore Hi equals He. The enthalpy remains constant, and therefore we made all the calculations and basically solved the problem. This is the very classic solution you would find to this problem. The question I want to ask now is that how much does the velocity change? How much? Are we in a position to calculate how much does the velocity change? Does the velocity change between the inlet and the exit? Between the inlet and the exit. Or let's put this question in a different way. How much should the area change for the velocity to remain constant? How much should the area change in order that the velocity remains constant? So this is the problem we want to look at very carefully now. And the answer is very simple. We learned that m dot I equals m dot E. The inlet mass equals the exit mass. Now, we can expand on this and write it in this way. AI VI divided by specific volume at inlet equals AE VE divided by VE. Now, we know the specific volumes, and we can answer these two questions. How much should the velocity change? So if we keep AI equals AE, we would know a ratio between inlet and exit velocities. And if we keep the velocities constant, then that would give us a ratio between inlet and outlet areas. Let's see what happens. We can write AE divided by AI equals VE divided by VI. And that is for the case that we want to VI equals VE. That's exactly the assumptions we made. And now we want to see the consequence of that assumption. Now, this equals, we know both specific volumes, that is 0.2597 divided by 0.00127. And the outcome for AE divided by AI is 230.43. And that's very interesting, because that means that if you want to keep the velocity constant, we have to increase area 230 times. That's a large, large value. It's not small. Or alternative, if you keep the area constant, the velocity would increase 230 times. It means that a 1 meter per second velocity at the inlet would end up 213 meters per second. That goes very much into the compressible range, 230 meters per second, which is quite a high velocity for an inlet velocity of 1 meters per second. Certainly, we have to be more careful in assuming the constant velocity and the conclusions it has, and we have to check it if that assumption uh, has any consequences on the geometry that we are designing or we are using, and this is a value. It's interesting to note that in many thermodynamic textbooks, when you see the problem of throttling, you wouldn't see a picture like this one. Quite often, what they do is that we have a line inlet, and then they draw a very large box, and there is some liquid at the bottom. There is a valve here, and there's a valve there. In fact, there are two exits, okay? There are two exits, which here, this is for liquid, and this is for vapor. So we have two different lines. What we could do is to write the mass conservation law in a more detailed way. What we do is that we write it 0 equals the inlet mass m dot I minus, there are two exit mass, one is the liquid and one is the vapor. So it is m dot E for liquid and minus m dot E for vapor. Okay, and now we could do the same practice for this equation, and it would end up as 0 equals AI v velocity times divided by a specific volume, area, velocity, a specific volume. It is rho AV, the very famous equation. We have replaced rho with a specific volume, and minus area for the liquid, velocity for the liquid, and VEF for the liquid, minus the same practice for vapor, VEV, and the specific volume. Okay. For equal velocities, if for equal velocities, what we could do is to simplify this equation and put numbers for specific volumes. This would be AI divided by 0.001127 minus AEF divided by 0.001043 minus and AEB, and that's divided by 1.6941. It's very much shows us that the inlet area and the area for the liquid would be fairly similar. They wouldn't be that different anyway. The real change comes when we are talking about the vapor area, and that area should be different. Otherwise, there would be very, very large velocities. This is a conclusion that we can make on the assumption that we had made about the um, equal velocities. Really, for such an expansion of this fluid of water, for other fluids it might be different. The area change should be very large to go along with the assumption that the velocity should remain the same. Another aspect of this problem, which has a lot to teach us, is when we look at the second law of thermodynamics for this valve. We all know that free expansion is one of the irreversible processes, and the entropy should increase. In fact, the entropy should be generated. If we should have a generation of entropy, and the exit entropy should be more the inlet entropy. Now, what we want to do now is to put numbers to that. And what I do first is that we know if we assume that m dot I is 1 kilograms per second, which means that I am doing this calculation for every kilograms per second of inlet fluid. Then m dot EV, which is the vapor, would be 0.1528 kilograms per second, because we know quality, so it's very easy to put a number to it, and m dot EF equals 0.8472 kilograms per second. So we have some order for the mass. The second law of thermodynamics, we could have a look at it here, and the second law tells us that the change of entropy inside the control volume, which would be zero because we are assuming the problem to be steady, the change of entropy inside the control volume equals the entropy that enters with the mass, the entropy that leaves with the mass that leaves, heat transfer divided by the boundary temperature, and the generated entropy. This is the second law of thermodynamics for the process. Now, for the time being, for our simple calculation, we assume that throttling valves are adiabatic, so this term vanishes, and we could write so this term and this term. The left-hand side vanishes since the problem is steady. This term vanishes since we are assuming that throttling valves are adiabatic, and therefore what we may write for the second law of thermodynamics is that 0 equals m dot I Si minus m dot E. Se plus q dot over Tb and plus S dot J. Let's get rid of this one since the problem is adiabatic. Divide everything by mass since m dot I equals m dot E, and the equation reduces to Si minus Se plus S dot Gen divided by m dot. 0 equals Si minus Se plus S dot John divided by M dot. And we have values for Si and Se. 0 equals 2.1381 minus 2.2282 plus S dot Gen divided by M dot. And the result would be S dot Gen divided by M dot equals 0.0901 kilojoules per kilograms Kelvin. All good and happy. S dot Gen is positive, and therefore the problem is possible. We have calculated the positive S dot Gen, so we could conclude that entropy is generated, the process is irreversible, and therefore it is a possible process. Well, before we leave this problem, there is still another question that we could answer it. And the question comes from the point that some liquid has vaporized. Where did the energy come from? It's just like evaporative coolers. The liquid vapors, and this energy comes from its surrounding. Here, the surrounding is the liquid that remains liquid. So, to show just this matter, what we do is to write the second law of thermodynamics for the liquid that remains liquid and for the liquid that becomes vapor. So the equation would look like this. 0 equals m dot I Si minus m dot E, which is in form of liquid, S E in the form of liquid, minus m dot E as vapor, and Se as vapor plus S dot Gen. We haven't changed much, but we have just separated, and we know that this m dot I equals the sum of these two m dots. So we can also write this equation as 0 equals m dot EF, that's the fluid that was the fluid and remained fluid, times Si minus SEF, and plus m dot EB times Si minus SEB. And this is the liquid that turned to vapor plus S dot Gen. And we have two values we have values for all these terms, and we just replace 0 equals 0.8472, which is the value for the liquid that remained liquid, times its initial entropy, which is 2.1381, minus its final entropy, which is 1.3028, plus now the mass that was liquid and turned to vapor, which is 0.1528 times 2.13 81 minus 7.3589 plus S dot J. So I elaborate on this and write it down. This term is the mass of water that was liquid and remained as liquid. The mass of water that was liquid and remained as liquid, and you can see that its entropy is reduced. And this term is the mass of water that was liquid but vaporized. The mass of water that was liquid but vaporized at the end. So just putting numbers to these terms and calculating them, 0 equals 0.70767 plus, and this term would be a minus 0.7977 plus S dot J. Bring these two terms to the other side. S dot J would equal 0.7977 minus 0.70767, which it means that this term belongs to this case, and this term belongs to this case. Now, although still we haven't changed much, but there is a point into this that when the water has vaporized, it has collected some energy to vaporize. Although this energy doesn't come from outside the Throttling valve, since the Throttling valve is adiabatic, nevertheless, it has to come from inside the valve, and so the vapor has collected this energy from the liquid. I mean, this one has collected this energy to vaporize from this sentence. And therefore, we expect that the water that was liquid and remained liquid has lost some entropy due to heat transfer, and the water that was liquid and vaporized has gained some entropy due to heat transfer, and that is different from the entropy generated. That is different from the entropy generated from irreversibilities. We have a little chance of calculating that exactly, but just an assumption, a very rough assumption of what number could that be could we give that case, and how much in fact how much transfer of entropy there was between these two terms, we could just assume some sort of Q dot over TB for this heat transfer. Now, the amount of heat transfer is the vapor's final enthalpy. If we assume that Q is the difference between enthalpies, then Q dot would be 2675 minus 762.51, which is the difference between initial and final enthalpies, just an assumption of the level of heat required, just an estimation. And we must multiply this by the by its mass, which is 0.1528, and divide it by the boundary temperature. We don't know what the boundary temperature is because the temperature is changing. Just let's take an average, and the average would be 412.9. And the result of this ratio is 0.707 kilojoules per Kelvin. Kilojoules per Kelvin. This is a very comparable number to the numbers we have here. It's not exactly this one, although it looks to be very similar, but it's not exactly this one. And these two are two different things. But certainly we can know that the change of entropy between saturated liquid at these two pressures is far less than the change of entropy that this liquid would require to vaporize. So a lot of this difference, we can assume has come from, in fact, the heat transfer that has happened between the liquid and its vapor. Okay. Thank you very much for listening. I hope you learned from this example, and cheers.